The answer to our YouTube title question unravels in the heart of our subject matter. The superheavy element, Oganesson 118, a behemoth with 118 protons and 176 neutrons in its most stable isotope. With more neutrons and protons than any other element, it's the heavyweight champion of the periodic table. Although scientists have only been able to make it exist for less than a second, its fleeting existence has significant implications. Let's take a journey into a world that teems with elements so heavy they defy our current understanding of physics. A world overflowing with matter that possesses properties so unique they could potentially revolutionize the way we perceive the universe. Welcome to the enigmatic realm of superheavy elements. Elements, or ishies, are those chemical elements that have atomic numbers greater than 104. They exist on the fringes of the periodic table, a place where the laws of chemistry and physics seem to waver. The sheer weight of these elements makes them highly unstable, often causing them to disintegrate in mere fractions of a second. The naming of superheavy elements is a fascinating process, steeped in scientific tradition. For instance, elements 116 to 121 are named after renowned scientists and places, with each name reflecting a unique story of scientific discovery. Livermorium, element 116, is named after the Lawrence Livermore National Laboratory, a prominent research institution in the United States. However, these elements are not just intriguing because of their names. It's their properties and potential uses that truly baffle scientists. While their observed properties are scarce due to their short lives, predicted properties paint a picture of substances with extraordinary potential. Yet these elements do not exist naturally on Earth. Their instability and short half-lives make their occurrence in nature virtually impossible. But could they exist naturally in other parts of the universe? It's a tantalizing question that feeds the curiosity of scientists worldwide. Oganesson, element 118, is the heaviest element ever created by humankind. Its existence, although fleeting, pushes the boundaries of what we know about the atomic world. But what does mean? And what is the difference between nanoseconds and milliseconds? As we delve deeper into the world of superheavy elements, we'll uncover these terms and more, guiding you through the intricacies of this complex and captivating scientific domain. So, what exactly are these superheavy elements, and why are they so fascinating? Stay tuned as we embark on this journey to explore the enigma of superheavy elements, their properties, potential uses, and the questions they pose about the universe at large. To understand superheavy elements, we first need to comprehend some fundamental scientific concepts. Firstly, half-life, the period required for half the atoms in a radioactive substance to decay. For example, possessing a kilogram of a radioactive element with a 1-year half-life would mean that you'd have half a kilogram remaining after a year. Secondly, units of time. A nanosecond equates to 1/1000th of a second, and a millisecond is 1,000th of a second. To give a familiar comparison, an eye blink lasts approximately 300 milliseconds. Now, we'll delve into the realm of superheavy elements, those from element 116 to 121. Superheavy elements are defined by an atomic number exceeding 104. Artificially created within labs as they are not naturally occurring on Earth, their half-life is noticeably short. Element 116, or Livermorium, named in honor of the Lawrence Livermore National Laboratory in California due to their significant contribution to its discovery, has a half-life in the millisecond range, rendering it highly unstable. Uranium holds the title for the heaviest stable element that we are presently aware of. However, there are elements that outweigh uranium. Welcome to the world of superheavy elements. These are the elements that possess atomic numbers from 116 to 121. Unlike the elements you encounter daily, these superheavy elements do not occur naturally on Earth. Instead, they are products of scientific experiments conducted in laboratories where scientists fuse lighter elements together. This process of fusion yields elements that boast significantly high atomic numbers, thus earning the moniker superheavy. However, these superheavy elements aren't naturally occurring due to their inherent instability. The nuclei of such elements are densely packed with protons and neutrons to the point of nearly disintegrating. This precarious state of instability triggers a process known as radioactive decay, where elements disintegrate spontaneously while emitting radiation. The decay duration, termed as half-life, of these super-heavy elements is astoundingly brief, with some lasting for just a fraction of a second. Now consider this. Could these super-heavy elements be naturally existing somewhere in the universe? It is plausible. The universe, with its vastness, might harbour conditions that appear extreme to us, but are actually ordinary. Perhaps in the throbbing core of a dying star, or amidst the disastrous collision of neutron stars, these super-heavy elements could come into existence. Super-heavy elements are not just heftier than other elements, they also possess unique properties. What makes these elements so distinct, you might ask? Let's explore. Super-heavy elements, those with atomic numbers from 116 to 121 and beyond, inhabit a captivating world of their own. They're the high performers of the periodic table, showcasing properties that are genuinely out of this world. Let's start with isotopes. Super-heavy elements possess a multitude of isotopes, each with a distinct number of neutrons. This results in various forms of the same element, each with its unique behavior and characteristics. It's akin to a family reunion where everyone shares the same last name, but each member has his/her individual idiosyncrasies. Now let's talk about stability. The heavier an element, the less stable it tends to be. Super-heavy elements are no different. They're more like shooting stars. They shine brightly but fade away rapidly. This characteristic is measured by their half-life, a term referencing the time it takes for half of a radioactive substance's sample to decay. For super-heavy elements, we're looking at times that are faster than the blink of an eye. For instance, element 118, Oganesson, the heaviest we've ever synthesized, possesses a half-life of less than a millisecond. Despite their instability, super-heavy elements are anticipated to have some isotopes that could be relatively stable, a phenomenon attributed to the island of stability. This term delineates a theory suggesting the possibility of a group of stable super-heavy elements somewhere in the broad spectrum of the periodic table. Now, why don't these elements naturally reside on Earth? Simply put, they're too heavy and unstable, but who knows? They might exist naturally in other corners of the universe. These unique properties make super-heavy elements potentially very useful, but how can we utilize them? Let's delve deeper into the intriguing world of super-heavy elements. The potential uses of super-heavy elements are as fascinating as the elements themselves. Let's delve into the world of super-heavy elements, particularly those from element 116 to 121, and explore their potential applications. Imagine for a moment a world where we can harness the power of these super-heavy elements. Their unique properties could open up a whole new realm of possibilities, especially in the field of energy production. For instance, these elements could offer a new and potentially more efficient source of nuclear energy. The energy produced from their decay could be harnessed and used to power everything from cities to spacecraft. However, the potential applications of super-heavy elements don't stop at energy production. Their large atomic size and high electron count mean they could also have unique chemical properties that we can exploit. These could range from creating new materials with never-seen-before properties to catalyzing chemical reactions that are currently impossible with lighter elements. In the field of medicine, super-heavy elements could also play a crucial role. Some isotopes of these elements could be used in medical imaging or even in targeted cancer treatments. In fact, the use of radioactive isotopes in medicine is not a new concept. For years, we've been using isotopes like technetium-99 for medical imaging and radium-223 for treating cancer. But what about the presence of these elements beyond our planet? Well, it's not entirely impossible. Some theories suggest that super-heavy elements might exist naturally in other parts of the universe or our galaxy. They could be formed in the extreme conditions of supernovae or star collisions, although we haven't found any concrete evidence yet. The heaviest element that we've ever created is Oganesson, element 118. However, it doesn't exist naturally, and its half-life is extremely brief. The world of super-heavy elements is full of mysteries and possibilities just waiting to be explored. The heaviest element ever created, Oganesson, element 118, takes the crown. Yes, that's right. Oganesson, named in honor of the Russian physicist Yuri Oganesson, a prominent contributor to the field of superheavy elements. Oganesson, a marvel in itself. It is a superheavy element that does not occur naturally on our planet. The reason for this is its incredibly brief half-life. In simple terms, half-life is the duration it takes for half of a sample of a radioactive substance to decay. For Oganesson, that half-life is less than a millisecond. Just like a flash, it disappears. But what does this decay mean for Oganesson? Essentially, decay is a process of transformation. Oganesson, due to its inherent instability, disintegrates into lighter elements, meanwhile releasing energy. It deviates from its group members in the noble gases group with its characteristics. It's predicted to be a solid at room temperature, not a gas. This is attributed to its colossal atomic mass that leads to a drastic increase in attractive forces among its atoms. Yet these are just conjectures, as Oganesson's brief existence poses great challenges to observation and verification of these properties. You might question, if it does not occur naturally and its lifespan is extremely short, what's the relevance? Here's the answer. The synthesis of super-heavy elements Oganesson aids in refining our comprehension of atomic theories and the forces that bind matter. It's thrilling to consider the island of stability, a theoretical area where super-heavy elements could have longer half-lives. If such an island is real, it could pave the way for a plethora of new prospects in the scientific and technological sectors. And what about alien environments? Is Oganesson's existence possible there? Theoretically, the answer is affirmative. For instance, in the harsh conditions of a supernova, the creation of super-heavy elements is plausible. But for now, it's just speculation. As the mysteries of their existence, fascinating properties, and potential uses unfurl, super-heavy elements like Oganesson truly stretch the limits of our scientific knowledge. The exploration of super-heavy elements doesn't stop here. The journey of discovery is far from over, and the future holds promising potential for new elements beyond the currently known 118. These new elements, starting from 119 and beyond, are uncharted territory, offering a world of potential for scientific exploration. The search for these super-heavy elements is a delicate dance of science, requiring precise techniques and advanced technology. The island of stability, a theoretical region where super-heavy elements could have longer half-lives, is one such area of interest. The term half-life refers to the time it takes for half of a given element's atoms to decay. For super-heavy elements, this duration is often minuscule. In the quest for elements from 116 to 121, scientists are not just seeking to fill the periodic table, but are also exploring their potential applications. These elements might have properties that could revolutionize fields like medicine, energy, or materials science. However, creating these elements and studying their properties is a complex task. Their high instability and quick decay rates make them challenging to work with. For instance, element 118, Oganesson, the heaviest element we have created, does not exist naturally on Earth due to its short half-life of less than a millisecond. But the question remains, might these elements exist naturally elsewhere in the universe? It's a tantalizing possibility that drives the curiosity of scientists and researchers. The future of super-heavy elements is a thrilling frontier, filled with challenges and opportunities. As we delve deeper into the heart of matter, we continue to push the boundaries of our understanding, unravel the mysteries of the universe, and challenge the limits of our knowledge. As we continue to explore the world of super-heavy elements, who knows what fascinating discoveries await us?